If you just joined us now, we are just trying to find out a little bit about what your teaching experience is in physics and whether you would regard yourself as a physics specialist, i.e. in a way, maybe having studied a physics degree or a degree that has a considerable physics element in it. But if you are just teaching physics as part of your normal science provision, you're very welcome as well. And I'm going to try and cater for both groups if I can. So I would say that what we're going to talk about today involves those three topics. So if you could give us a rating of what you feel in terms of how confident you are in terms of teaching forces up to the level that you normally teach it, pressure and particle theory. And I love the confidence in the group to start with. That started really confident and becoming not so confident anymore. So that's really nice to see. As you're seeing Menti, if you want to use things like this in your classroom, they are really useful. You can use it with loads of different topics and activities. You can make your own Menti activities like the one I'm using today at mentimeter.com. So if you go to mentimeter.com, it's free to log in, to register, and then you can use it with your students as well. So I wanted to start with something that is around us all the time. As you well know, we are literally surrounded by an ocean of gas around us. The atmosphere is literally a massive ocean of gas that is surrounding us. And so above us, we have tons and tons of air that is constantly pressing on us. And there's a lovely demonstration that you can do with this. And Keith Gibbs, if you know his work, is fantastic for this sort of little demonstrations that really make the kids think. He does this really well. So I want to share this one with you. Basically, we have a sheet of newspaper on my desk. And underneath, I put a CD that is being held by this string with a large paper clip at the bottom. So what we're going to do is we're going to make sure that this is nice and flat on the surface of my table. And I'm going to try and pull up this sheet of paper as hard and as quick as I can. Now, you probably know what is going to happen, but if you want to tell us on the chat what you think is going to happen, that would be nice before we actually reveal the trick, if we can call it a trick. So let's see what you're thinking. What's going to happen when I try to pull up the string as hard as I can? Please give us your things your answers on the chat. So Jess, is the string attached to the CD? Yes, the string is attached to the CD. So the CD will be lifted up as the string is lifting. Yes, okay, so Stuart thinks it's going to be very hard because the air pressure on the large sheet of newspaper. Well, I do tend to agree with that. Well, we'll see what happens. Yeah, it's actually really, really hard. So if I try to pull it, it's really, really hard. It doesn't come up at all. You really need a lot of force to do this. And I cannot do it. It'll probably more easily break the paper than lift the whole thing up. And the reason is what we just said earlier. We've got a massive amount of air molecules basically pressing down on my sheet. And if you know anything about air pressure, we know that there is 1 atmosphere of air pressure on near the surface of the Earth on sea level. That basically means about 100,000 pascals. If you know what a pascal is, it's newtons per meter squared. So essentially, we are saying that for every meter squared of area, of the surface of the area on the ground, we have 100,000 newtons pressing down on that. And if you look at my sheet here, I had to cut it a little bit to make it fit on my desk, but this is roughly half a meter squared. So that means that we would have about 50,000 newtons of force on this sheet of paper. Now that is the equivalent of about 5,000 kilograms sitting on this, or 5 tons. Really nicely. So this idea that the pressure in a fluid is dependent on the depth or that you are in the fluid, and basically the height of the column of fluid above you at any particular point. So if you show the kids a pressure from your pressure gauge in your phone, if you have a pressure gauge in your phone. This is my iPhone, and I'm using the Firefox app. So it's on this iPhone here, and on this app you can basically use the pressure gauge inside your phone, and you can plot the pressure on that gauge. So I'll let it settle a little bit, but then what you could ask your kids is, well, what's going to happen if I now lift the phone above the desk and I lift it above my head up here? What's going to happen to that value of pressure that we see on the app at the moment? Again, I would like some ideas from the chat, if possible. So what do you think is going to happen? Is the pressure going to increase or decrease? I'm not sure why it is increasing at the moment like that, but it's the pressure going to increase or decrease when I lift the phone? Okay, Tamara says decrease. Okay, let's have a look. So you obviously you do know this, but yeah, even a small change in altitude, okay, should cause a change in the pressure. Okay, it just took a little bit to pick up, and when I put it back down, you should see it increases again. So yeah, the process has started, so hopefully you can see it now. And like we did before, you can see that this cup here is now filling, and this time I think it's a little bit more noticeable that the level of water is rising at a lower and lower rate as the column increases. Okay, so we've got that this time, again, we've got something very similar, but the water is taking a different path. And for kids, this is going to be very unintuitive. So why on earth is this happening? So again, if we look at our slides, what we can see on this one now is that initially we have a lot of water on this side. So provided that we have filled the straw with water, what we will have is that the same pressure on this point, because of the column of water above, would be the same pressure at that point. So there is a pressure pushing on the water inside the straw, and that is transmitted in all directions throughout the straw, which is what causes the cups to fill. And again, unsurprisingly, when you've got the same level of water on both sides, then you have the same pressure on both sides, and so there is no more transfer of water from one to the other. It takes us quite nicely to our make and take experiment, which is very, very simple. It's a little Pythagoras cup. So there you go, just make your way through. Right, so now I have my lovely Pythagoras cup, and I'm going to test it with some liquid. Fill your cup up to nearly the point where the bend is in the straw. You're okay. Go over there, and your cup is going to empty audio. Cut it.